recordings, I created the video for lab number 2 and went back to view it and had a couple of technical problems that I'm working on. So everything's in the Blackboard folder for lab number 2 except the video. So as soon as we finish here, I'll make a concerted effort on that. And hopefully within an hour or so, I'll have the video posted. Probably since I'm late with it, I'll send everybody an email so that you'll know when it's available in Blackboard. And then all the information you need will be right there. Okay, so for today, we've got exam number 2 review on chapter 12, chemical kinetics. And the review document for this one was rather short, it would appear, but if you start digging into the problems, you find that each problem takes a little doing to get the answer. So it's not as short as it looks. The first problem probably should have been moved to later in the review document because it jumps right into mechanisms. And mechanisms can be tricky. We probably want to review some other things before we get to that one. There's Kessa. Okay. Okay, we're all here, and it looks like Kessa's behind the wheel.
Yeah, I gotta go over to my mom.
Okay, you're parked, I hope.
I'm used setting up on my dash. It's attached to my dash thing.
Okay. Fortunately, there's no, well, there may be interaction required. So if you have to ask a question, you probably want to pull over and do that.
Oh, it's only like a 5-minute drive. It's not far.
Okay.
Yeah,
right.
I'll be getting out of the car here in just a minute.
So we'll get started with our review. And I was just saying, I want to, number 1 in the review might give you some trouble, but I'd like to hold that one till later because it talks about mechanisms. And instead, go to some of the later ones. At least skip to let's see, yeah, number 2 or later. So if anybody has any particular one that's giving you trouble, let's get those out of the way. And then if needed, I'll start talking about items that I think are more important, particularly the method of initial rates. We didn't have a chance during the lecture to go through the actual working out of initial rates problem. So I think it would be good for us to spend some time on that. But if there are any other things that are bothering you before we get to that one, then we'll definitely deal with that. So the floor is open for any questions. Okay, if not, of course, if anything comes to mind while we're talking, feel free to interrupt. So let's look at, does everybody have a copy? So I don't want to have to share the screen for the review document. So everybody has a hard copy in front of you of the review. So I can just reference the number of the problem that we're dealing with and go from there. Let's look at rate laws and the generic rate law. Before I get to a specific problem, the generic rate law is going to be something of the form of your rate constant and then the concentration of one of the reactants and its order, and then another reactant and maybe its order, and maybe you have a third reactant. That's entirely possible. NM, let's make that one O. Okay, so in order to describe the rate, the differential rate equation for a reaction, you need all the reactants, their concentration terms, right? There won't be a value in here until you resolve the equation, but whatever that happens to be, and then these will actually be numbers. Now, I've said it before, they don't have to be whole numbers. It's better if they are whole numbers because it's easier to understand a whole number order than it is a fractional order. And anytime I give you a problem to work out in an exam, you can be assured that the whole numbers will prevail. So for problem number 2, what we have here is ABC reactants, and the orders are going to be 2, 1, and 2. So we don't have to write the 1 in there, because if you got the term, it's got to be 1 or something else. It can't be 0. If it's 0, that term goes away, right? Because anything to the 0 power is 1. So this is our rate expression, and then the question is, what's the overall order of the reaction? Right? Remember, the overall order is just the sum of the individual orders. So the overall is just 2 plus 1 plus 2, right? And it's easy to miss that middle one, right? Because you don't have a number staring you in the face. So if you're calculating an overall order and there's a term there, and it doesn't have a number, it is automatically 1. So 2 plus 1 plus 2 is 5. Right? So the overall order for that one is 5. I doubt if that one gave too many people trouble, but it's worth looking at. Okay. Well, that was number 2 on our review document. All right. Now let's just take them in order. Number 3. We'll take them in order until we find one that's a repetition, if there are any. If we're repeating, if one comes up and repeats something we've already done, we'll skip it. So number 3 says, if the reaction of this H2 plus I2, so there's your reaction, then is second order, which of the following will yield the linear plot? So we've only got one reactant, and we usually express rate equations in terms of disappearance of reactant. Right? So with only one, then we have one reactant, and we've studied 3 to choose from. Right? So which one would lend the linear plot if you're told that it's second order in hydrogen iodide? Well, we know that if we plot that against time versus that gives us linear if it's 0 order. Time versus natural log gives us first order. And second order then would be inverse. So our choices there would mean that B, the inverse plot, would be linear for second order in hydrogen iodide concentration. Okay. Number 4 talks about enzymes as catalysts. Now, we didn't spend a lot of time on enzymes in the lecture, but your textbook does have some information concerning that. So which one of the following is incorrect about enzymes? Well, let's see. A says they're usually proteins that catalyze specific biological reactions. That's true. Most enzymes are proteins. There are some enzymes that are nucleic acids, but they're rare and very specialized, but they're still, the statement is true because it says usually. B says they're equal to inorganic catalysts in efficiency. That's false. Enzymes are, in fact, much, much, much more efficient at catalyzing reactions than inorganic catalysts are. And we really don't have time to discuss why that is, but just take my word for it. It's a good thing that enzymes are very efficient. Otherwise, our bodies wouldn't function very well. So what do we mean by efficiency then? Right. Efficiency is in terms of how many reactants can be catalyzed in a period of time by a given catalyst, a given amount of catalyst. And the fact of the matter is that enzymes will catalyze reactions, not only more reactants will be converted to products over a period of time. Well, that's over a period of time would be faster. So that's another way of putting it. Enzymes tend to catalyze reactions much quicker. They lower the activation energy, and that references the way that enzymes work as opposed to inorganic catalysts. So that's about all I can say about that one. Now, since one of our options in number 4 is all of these are correct, then we found the one that's not correct, B. So that means that C and D must be correct, and in fact they are. Several thousand are now known. Right? Several thousand enzymes are now known. Molecules they react with are called substrates. Right? So that's terminology. Okay, so that's number 4. I made passing reference in the lecture to free radicals. So this is a question, number 5, about free radicals. So free radicals are a type of, they can either be elements or they can be compounds. And for a free radical to be such, it's not A, unconventional political views. That's just a filler. B, positive charge. Free radicals they can have a charge, but they don't have to have a charge. That's not the definition of a free radical. So they could be charged, they could be positive charge, they could be negative charge. So that does not define a free radical. A free radical is defined by D, an unpaired electron. So if you have an electron that's not paired, that's considered a free radical. And it can be neutral. An oxygen atom is a free radical but it's not the definition of a free radical. Remember, oxygen atoms, if we look at their valence electron structure, they have six electrons. Right? So if we do a Lewis diagram, that means they've got two unpaired electrons. So the oxygen atom is a free radical. And that's one of the reasons that they're driven to be diatomic. They react with one another. Since their free radicals are extremely reactive, one oxygen reacts with another one and makes a stable O2. The other diatomics react for the same reason. Okay, that was 5. Let's see, 6. This is a good one. So if you're given the rate law, in this case, rate equals K, and A, B. So A is the first order, B is second order. We have two reactants in this chemical equation. If the initial concentration of B is increased from 0.1 to 0.4, 0.1 to 0.4. Right? So initially, the rate is defined by whatever A is, and B is 0.1. If we increase 0.1 to 0.4, how many times did we increase that concentration? 4 times. 4 times the increase. So how much faster will the rate be if we increase the concentration of B by 4 times? Well, everything inside those brackets is squared. Right? So 4 has to be squared to 16 times effect on the rate. Okay, that's why the answer is C. If the problem had said not just increase B, but let's say we increase A. Increase A from 0.1 to 0.4. Okay, that's 4 times. But it's to the first power. So it's just 4 times, and 16 times would be 64 times. So if we quadruple both of them, the effect would be 64 times increase in the rate. Okay? That's a lesson in interpretation of the differential rate equation. Okay, that was 6. How about, oh, this is a good one. It's kind of a trick question. But I did hammer this topic quite a bit during the lecture. For which of the order reactions is half-life of the reaction proportional to 1 over K, where K is the rate constant? So let's say we have first order, second order, excuse me. All right, again, 0 order, first order, second order. Right? And we have a rate. So what is the half-life expression for the 0 order? Let's see. Yeah. 0 order. Well, I thought I had, do I have the right? Should have the right one. Hold on a second. Okay. So recall the half-life expression. Actually, I shouldn't say rate. I should say half-life. T1 half. For the zero order is let's see, 2K. Oops. The concentration here. Okay. The half-life for the first order is divided by K, and this is 0.693, I believe. Yep. And this one is 1 over times K. All right, so then go back to the question. Which of the following of the half-lives are proportional to 1 over K? The answer is they all are. Every one is proportional to the inverse of K. So that's why for 7, the answer is D. All right. How about, let's see. I think I'm looking at the wrong document. That's the problem. I'm not synchronized. You're probably asking yourself the same question. What is he talking about?
There are some questions that are the same.
Yeah. I just got the numbering wrong. I was using the wrong reference numbers. So let's try, let's see. Okay, now I'm on track. Number 6 then. Number 6 references these two equations in a mechanism, right, for step 1 and step 2. So this one plus this one yields this one plus this one, and that one plus that one yields that one. Oh, and the overall reaction is this. There. So this is the mechanism. And we're also told that this is slow. This is very slow. Right, so this is really just a question as to whether you understand when you propose a mechanism, which is the rate determining step. And even if they're all slow, one of them's got to be the slowest. And in this case, step 1 is the rate determining step because it's very slow, not just slow. Okay, and we could write the rate equation using that step for this one, right? That's not part of the problem, but I figure, you know, why not use it? So if we use this to determine the rate determining step, the rate equation for the overall reaction, we can use A and B, which would be rate equals some K value, which for step 1 would be that. And remember, concentration of A, concentration of A, actually that species and this species, and they're both coefficients of 1. Remember, in the steps we can use the coefficients as orders. So this would be the rate expression for the overall equation. And since A and B are part of the very slowest step, plus they're also in the overall rate expression, that's our rate equation for this reaction. It's not like the one we had before where we had a species in here that was intermediate, right? We had to correct for it. We did that in the lecture. But in this one, we're done. That's the rate expression for this reaction based on that mechanism. Okay. All right, let's see. That was 6. All right, let's skip 7 for now. We'll come back to that one. I want to do one with, well, let's get some more theory out of the way first. For numbers 8 and 9, we have this chart, or actually an energy diagram, that starts off low and ends up high. Okay. So this is the energy level, and this is the reaction progress. Okay. So the distance between here and here is given the letter A. The distance from here to here is given the letter B. The distance from there to there is given the letter C. And then we have another possible energy curve that is given here to here as E, and then we have D. Okay, so here to here is D. So that difference to that difference is D. And the question is, which letter shows the activation energy without the use of the catalyst? If you have no catalyst, it's going to be the higher amount of energy required to get the reaction to go, to reach the activated complex up here. So from here to here, A is the activation energy for uncatalyzed reaction. Then number 9, that was 8. So 8 would be 8. And 9 asks the same question for the one using the catalyst. Right? So E is the one for the amount of energy required, the activation energy for the catalyzed reaction. Okay? So one of these others has a significant role to play, and that's D. That's the enthalpy of the reaction. And it's going to be endothermic because the products have more energy stored in them than the reactants. Okay? All right. Oh, number 10 is a good one. We can digress into mechanisms long enough to talk about number 10. Right, so number 10, the overall reaction is this. That's the overall reaction for the decomposition of hydrogen peroxide. Right? It changes to water and oxygen. The proposed mechanism says, step 1, for the catalyzed reaction, we're saying that iodide ion yields water plus IO minus. And then we take another one, right? There are two of them in this reaction. And we combine that with IO minus to yield water, oxygen, and iodine. The question is, what's the catalyst? Right? Remember the definition of a catalyst. It enters into the reaction, but it's not consumed by the reaction. So you look for the one that goes in one end and comes out unchanged on the other end. So in that case, hydrogen peroxide does not come out unchanged, right? The iodate, the IO minus ion, is produced in the reaction, so we never know it's there. Catalysts we know are there because we put them there. So the only one left is the iodide ion. It goes in this end, comes out that end. That's your catalyst. Right there. Now that's an inorganic catalyst. Organic catalyst is an enzyme called catalase. Every cell has catalase in it. Doesn't matter what. So eukaryotic cell, a bacterium, they have catalase in them. And they catalyze the breakdown of hydrogen peroxide. They do that because hydrogen peroxide is very reactive and it can damage the cells. So they need to be, hydrogen peroxide, when it's produced, needs to be done away with. But when you put hydrogen peroxide on a wound, there are broken cells there in that wound, which exposes the catalase. That's why when you put hydrogen peroxide on your wound, it fizzes. And in the process, it produces a lot of oxygen. And oxygen in itself is reactive. It's just not as reactive as hydrogen peroxide. That's why you only use hydrogen peroxide on a wound one time, just to clean the wound. It will kill all the bacteria because most bacteria don't like oxygen. But after you've sterilized the wound with hydrogen peroxide, then you treat it more gently with some sort of topical antibiotic or cover the wound, whatever it happens to be. But in that case, catalase would be the catalyst or the enzyme in that case. Okay. Now let's see if we can find a reaction. Here we go. Let's see. That one's kind of complicated. Let me see if there's a simpler one. No, looks like we're going to have to use that number 15. Let's see another one. Number 2 would work. Okay. Let's see what 15 looks like. It's going to take some work, but it'll be worth it. All right. So I'm not going to write this whole data set up here, but I will, for number 15, point out that in the data set, you have 1, 2, 3, 4, 5, 6, 7 experiments. Each of these rows is a separate experiment. And what's determined is, as a consequence of these concentrations of the reactants, in the first one, selenous acid, hydrogen ions, and iodide ions are the reactants. And the rate is determined, right? They would be, well, I can write the rate law, right? Because we know that we have a value for K. We have H2SO3 to some order, H plus to some order, and iodide ion to some order. Okay. So that would be the rate law without the actual values in it, right? So the question is, what's the numerical value for the rate constant? We're looking for that one. In order to do that, we have to determine what these values are here. And the reason for that is, in order to solve for K, we need to know what this term is, what that term is, what that term is, and what this term is from any one of these experiments. Then we have K as one unknown. So we have to find out what these are and apply that knowledge to one equation to solve for K. Right. So the simplest way to deal with this one is assign a rate or reaction number to each one, just sequentially from top to bottom, 1, 2, 3, 4. You would just go down, use a pencil. You would just go down and identify each one, 1, 2, 3, 4, 5, 6, and 7. Then when we write our calculations up here, we can just reference the rates for that particular reaction. All right, so what do we get? Well, the way to deal with initial rate data like this is to find two reactions where the concentrations are the same for all of the reactants except for one, and let one vary, keep the others constant. Right? So if we were going to do selenous acid, we're going to determine the M first, then we would pick two reactants, reaction experiments in which hydrogen ions and iodide ions were constant, and where selenous acid was allowed to change. Number 1 and 2, right off the bat, we got 1 and 2 that we can use to ratio. So, which one do you put on top when you ratio the reactions? We're going to take this expression and we're going to plug in numbers that we know. Right? We know this one, we know the rate, we know the concentrations of this one, this one, this one, and we leave that one blank because we don't know it yet. So if we were to do a ratio for the first one, we would say, look at the values. You want to ratio one on top of the other so that you get a non-fraction, right? You want a whole number, if possible. So you don't want to put the small one on top. So in this case, if we put 2 over 1, so rate 2 divided by rate 1 would then be the whole expression for rate 2. Well, actually, what we want is, okay, we'll deal with that. Then we would put 2 on the top, which would be K, and then the concentration of H2SO3 for 2 is 2 times 10 to the minus 4 to the M power. We don't know that one yet. And I'll fill these all in for, at least for this one. And this one's 2 times 10 to the minus 2 to the N, and I, oops, I need a number there. And I is 2 times 10 to the minus 2. For rate 1, we have a change in selenous acid. We have 1 times 10 to the minus 4 to the M power. And then we have the same thing for each one of these, right? That's why we chose them to not change. Okay? And then we have rates in here. So let's put the rate for 2 is, the rate for 2 is 3.33 times 10 to the minus 7. And the rate for 1.66 times 10 to the minus 7. Okay, so now we have our, this is going to solve for us what is M, right? So this resolves to what? Well, I need my calculator. So if we take this one and exponent 7, and then this one, exponent 7, divide, that's 2.006. Okay. Notice here, K's on the top, K's on the bottom. They cancel. This is the same as that one. It cancels. Same there, it cancels. So now all we have is this ratio. So what's 1 times 10 to the minus 4th divided into 2 times 10 to the minus 4th is 2 to the M power. So what power of 2 will give you 2? 1. Right. So now we have 1. That solves for this one. You do the same thing for the others. And let's see. Where do we have? Okay, we could do for the next one, for this one, we could do rate 4 divided by rate 1. Okay. And the K's are going to cancel again. The H2SO3s are going to cancel because they're the same. The iodides are going to cancel, so all we're left now with is the H's. Right? And we fill in the values for rate 4 is H is 4 times 10 to the minus 2 to the N power. And the first one is 2 times 10 to the minus 2 to the N power. And then we need to put in values for the rate. So the rate of experiment 4 is 6.66 times 10 to the minus 7. And the rate 1 is 1.66 times 10 to the minus 7. And 1.66 into 666 is 4. So that's 4 is equal to this one, which is 2 to the N power. So N would be 2. Right? You have to square 2 to get 4. So in that one, N is equal to 2. So now we know that this one is 1 and this one is 2. And O is a bad choice because that makes you think it's 0 order, but O is a variable. Right, so if we went in and did the same thing, let me make room now. You'll notice from the worked problems, handwritten, that I'm using different equations, right, than the ones that are given in the worked problems. But we're going to come out with the same answer. Let's see, I'm going to erase that one. Keep that one. Now we want to pick experiments where I changes and these two don't change. Okay? So we'll look at our data set and see. We want I to change. So 6 and 7 changes. 1 through 5 are the same. So we could compare. We need to look to see. 1 and 6. Right? So rate 6 divided by rate 1 would give us cancel the K's, right? Cancel these, they're the same, right? Between 1 and 7, it's the same. No, wait a minute, 1 and 6, excuse me, 1 and 6. H doesn't change between 1 and 6, but iodide does change. And iodide happens to be 4 times 10 to the minus 2 divided by, let's see, getting ahead of myself. That cancels, that cancels, that cancels, leaves us with that, but we need the rate. Right, so 6 is 13.4 times 10 to the minus 7, which is not scientific notation, but it makes things more convenient because those cancel and you just divide this into that. All right, so what's the concentration that goes with each one of those? 4 times 10 to the minus 2, and experiment 1 is 2 times 10 to the minus 2. And these are to the O power. Right? So that 2 into 2 is 2 to the O power, and this 13.4 divided by 1.66 is 8. Right? So what power of 2 gives you 8? O is equal to 3. Right? 2 cubed is 8. So now we know that this one is 3. Okay, we've got all of our orders together. Now all we have to do is pick a rate, any one of the experiments, and plug in the values for the concentrations that go with that experiment. And use the powers, the orders, and solve for your unknown. So let's just keep it simple. Let's do number 1. 1.66 times 10 to the minus 7 equals K, and this concentration is 1 times 10 to the minus 4 to the first power. Hydrogen is 2 times 10 to the minus 2 to the second power. And iodide is 2 times 10 to the minus 2 to the third power. Right, so now we have an equation with one unknown, and all we have to do is solve for it. So we keep K here, we take this one, this one, this one, put them over here in the denominator, and our calculation then would be 1.66 exponent 7, and then this one to the first power, divide by that one, and this one has to be squared. 2 exponent there, and let's square it. There it is. And then divide. So I got that much. Now take this one to the third power. And enter There it is. Okay, and then divide. So what I get is, I did that right. I get 5.1875 times 10 to the 5th power. And we've only got 2 significant figures in here. That's 3, but these are only 2. I just left off the decimals there. So rounding this off is 5.2 times 10 to the 5th is our K value. And that would be A. So even though I used different sets of experiments than the one that's given in the handwritten document, I get the same answer. Okay, any questions? It took a long time, but that's how you do initial rate experiments. Did I see a hand go up or just a flash? It must have been a flash. Okay, we're doing good on time. So that is a lot of effort just to get one answer. But at least you didn't have to do 7 experiments to get the data. The data is given to you. What do you do with the data once you got it? See, that was 15. Let's do 16. This uses half-lives to solve for K, right? So there's more than one way to approach this problem. And I never say there's no more than one way to skin a cat because I like cats. 16. All right, so for the reaction of A yields products, okay, we're given that the initial concentration is 4.2 molar. We didn't do this one in, we did one like it, I think, in the lecture. Hope it's not exactly the same one because I don't want to bore you. All right, so that's given, and the 2 half-lives are, first half-life is Q1/2 equals 56 for that concentration, and then the second half-life is 28 minutes. Okay, so there's our data. Now I've got to make room for, I'm going to build a table. Using this information. Understanding what we mean here is important to building the table, the actual data table. Right. So for 16, we've got time and concentration of A. Right? So at time 0, the concentration of A is 4.2 molar. Okay. First half-life, which means that the concentration will decrease to half that value. So the first half-life occurs at 56 minutes. Right? So we went from 0 to 56 and lost half. Second half-life is 28 minutes. So that means the concentration is now going to be 1.5, right? No, 1.55. There we go. Is that right? No, that's not right. 1.05. There we go. Add these together and get that. Add those together. There we go. But the absolute time interval that has passed is actually, let's see, 84 minutes. Okay, so there's our data table. Let's see. Yeah. There we go. No, I'm looking at the wrong one. Okay, here we go. Now, so what's the question? All right, you always have to figure what's the question. Calculate K without units. So what we need to do is we've got to decide what is the order of A, right? In order to make the calculation, we've got to know which half-life equation to use, right? Because we've got 3 different half-life equations and we need to know what the order is. Well, you have 2 possibilities. You can treat this data set just as is and do the transformations, right? A, log A, reciprocal A. Plot them and find out what the order is. Or you can calculate the K for each of them as if it were 0 order, first order, second order, and then compare the K values for this one and that one, right? K is a constant. So if we calculate 0 order half-life and do the K for this one, and you get 2 different K values, you know it's not the right one, right? So in my mind, that would be simpler than trying to graph it in the middle of an exam. So this is what I would do. I would do T1/2 for 0 order. So that would be T1/2 is, for the first one, is 56 minutes. And that's equal to concentration of A over 2K, I believe. Did I get, yeah, that's right. So we plug in the initial concentration here, 4.2, and then solve for K. Right. Actually, I think in the review document worked problems, I did it the hard way. This is an easier way, I think. So we're going to solve for K. So we put the 2K over here and the 56 over there. 4.2 divided by 56, and then divided by 2 is 3.75 times 10 to the minus 2. Now if we do it for the second half-life, 28, then the concentration is, initial concentration for the second half-life is this one, 2.1 divided by 2K. So now the K for this one would be 8 divided 2 divided. This one is 3.75 times 10 to the 2. So that tells me that this is 0 order, right? Is that the right answer? Well, is that the answer that's given here? Well, if it's 0 order, then, well, the nearest answer is C, which is the one that's given. So that's good. You don't even have to do first order, second order calculations, right? Because this calculation gives you the same K for both half-lives. Any questions? All right. Maybe I need to redo the work problems in this one, make them a little easier. Okay. Let's see. Okay. 17. See if I did that one easy or hard. Ooh, let's come back to that one. Let's look at mechanisms. I need to take a bathroom break. I'll be right back. I'm going to pause the video, and I hope I remember to restart. I forgot to start the recording back.
So you said no matter what, it'll always be in joules over mole?
Yes, because the universal gas constant is in terms of joules per mole K.
Mm-hmm.
The activation energy then has to be in joules in order for these two to cancel.
Cancel out. Okay.
Yeah. Okay, so I apologize. What did we miss? What did I do that we missed? I wasn't recording. We missed a lot. I apologize for that. It's just par for the course. Okay, for this one, number 18, we've got our Arrhenius equation, the integrated Arrhenius equation, because we need both temperatures. And then we're looking for that ratio, right? So we need to resolve this one over here. So the inverse of 300, inverse, and then the inverse of 310, and subtract those two. This yields 1.0753 times 10 to the minus 4th. And then this one becomes 98,000 and 8.314. This one becomes 1.1787 times 10 to the 4th. And we'll multiply those two together. And that gives us 1.26746. Anybody who knows me knows that I never throw decimals away until I have to. So we're going to keep all those decimals. And now we have this expression, the ratio of the final to the initial is equal to that. So how do we resolve that? Well, we take the antilog of this number will give us that number. And the antilog of the ln, or the natural log, on your calculator is e to the x. So e to that power is this value. Right, so I've already got it in my calculator. I'm just going to punch in, there it is, e to the x. Right. So now this ratio is equal to 3.5518. Now the question asked to the nearest whole number. Right? So you just have to remember your rounding laws. If you're going to the whole number, that means you're looking at this one and then the very next one to the right. Right? And our rules say if it's 5 or greater, you round up. So this rounded is 4. That's why D is the answer to 18. I'm trying to find the one that I missed recording. Oh, okay, I know. It was a rate expression, number 7, wasn't it? Okay. So maybe what I'll do is when we finish up, I'll go back and redo number 7, just so it'll be in the permanent record. Let me make myself a note here. Okay. All right. So any questions so far? That's one use of the Arrhenius equation. And the Arrhenius equation is given in your useful information. Right? So when you take the exam, there will be a document in there within that folder that has the Arrhenius equation. Let's see. Let me look at the other one that had temperature involved and see if it's worth tackling. Actually, 19 and 20 are both related to Arrhenius. No, 20 is not Arrhenius. There's temperature involved, but the temperature is just there to give you conditions for the reaction. It's not involved in the calculation. 19, however, is an Arrhenius equation. So let's do 19, since we're on that topic. And I can tell you right off that we're going to need the Arrhenius equation. Right? So we need 19. Let's see how it's given. Well, let's do what information are we given for this reaction? The second order reaction, and I'm not going to write the reaction up there. The rate constant has been measured to be at a temperature of 298 K. The rate constant for that one is 1.08 times 10 to the 7th. And the activation energy for this one, actually for the reaction, let's put it up here. It's not particular to that temperature. So the activation energy was measured at 11.4 kilojoules per mole. Okay, that's given. And it tells us this is valid over the temperature range of 195 to 304. That's important because we want to know what's the rate constant for T of 233. Okay. So we want to know what's the K. Be consistent. Okay. Equals what? Okay. So let's make the higher temperature the K2, the 2, and the lower temperature the 1. I think the calculations are easier that way. It should work either way, as long as you get the Arrhenius equation set up correctly. So the Arrhenius equation then says the natural log of K2 over K1 equals the activation energy divided by R. It's the same R as we used before. And then 1 divided by T1 minus 1 divided by T2. Okay? So we're solving for this one right here. So how are you going to get that? We can put the information in here, no problem. But then how do you resolve this? Well, you have to remember your log transformations, your log rules. And we can do that right now. The log of a quotient is equal to the log of the numerator minus the log of the denominator. That's what that is equivalent to. Okay. Then we can plug in let's go ahead and plug in the K2. This is 1.08 times 10 to the 7th. Right? So the log of that. And then this is our unknown. And then the activation energy is 11.4 kilojoules. Right? So there you go. You got to change it. 11,400 kilojoules per mole, and then 8.3145. And I'm leaving out the units just because there's not a lot of space. And then we have 1 over T1, which is this one, minus 1 over T2, which is this one. Okay. Now we have an equation in one unknown, and that means we can solve it. All right, so let's resolve this side. 233, take the inverse of that. And then 298, take the inverse of that and subtract the 2. Then multiply times 11,400 and divide by 8.3145. Oops. 8.31. Is that right? Yeah. So on this side, we have 1.28354. And on this side now, that's minus, we have the log of that value, the natural log of 1.08 times 10 to the 7th, and we take the natural log. This one then is 16.1951 minus log of K1. So now we want to get rid of that negative sign. And we can do it now, or we can do it later. Let's do it step at a time. Negative log of K1 equals this one minus that one. Right. So this one's minus 14.9115. And then negative on that side, negative on that side, just make them both plus, we're good. Now, e to that power, e to the x, the anti-log, is equal to K1. So we got that value, and we need to make e to the x. Here it is. So that's equal to 2.99 times 10 to the 6th power. And that would be, answer for that one is C. Okay? So what's the trick here? Well, there's several. One, of course, is you have to realize that you need to use this. Then assign your T1, T2s. Then the next trick that can throw you off is converting 11.4 to 11,400. That will mess you up if you forget to do that. And then, actually, the first one we did, but finally, is what is the log of a quotient? What does it mean? If you don't know that, then you'll never be able to solve for the K1 because you can't get those two logs separated. Okay? Let's see if I've missed anything of importance here that we need to go back to. One second. Just checking myself. Okay, I've got one possible here that is that I failed to put in the review document, and I think it's important. So let me let me talk about this one. It won't have a number because it's not in the review document. But it has to do with graphical interpretation of data. And that's a skill that is good to have. So if you see a graph like this, right? And you've got, let's make up some numbers. Let's see. There's the origin. There's time in seconds. And on this axis, we have a natural log of some value. And let's say when we plot that, we get a straight line. Okay. So with just that information, what can we say about the graph? Or about the reaction itself? What's the order of A? First order, right? Because it's the natural log of A. Even if we didn't have that there, right there, if we had this one, then you'd know that it's second order, because straight lines for zero are this way, straight lines for first order transformation, natural log, is this way, straight line for inverse is that way, which means second order. But in this case, no, it goes that way. Now let's say we're given an equation that, let's see. Well, we've already solved one problem. We know what the order is, right? First order. Just by looking at the y-axis, and it's a straight line. It's got to be first order. Second is, let's say we're given the equation for that line. So y, which would be this, equals, let's make up a slope, say minus 3x plus, well, let's say minus 3x, let's say minus 7 times 10 to the minus 5th. Let's make something up. So this is the y-intercept right here. Right? So that's going to be 7 times 10 to the minus 5. The slope of the line is what? The slope is equal to minus k. So k is equal to 3. So if the question is, what's the value of k? You know from the first order reaction, actually, no, wrong. Nobody caught me on it. If y is the log of a, what is the slope? The slope is minus k times t, right? Well, I was half right. The slope is equal to, in this case, we said 3. Right? So slope would be minus 3. Then k would be 3. That's true. So I had it right to begin with. I just confused myself. So that's interpreting a graph. Right? So if you're given these features and that equation, then you get a lot of information from that. In fact, when you do your labs and you plot out your values and you determine which one is which, then you graph it, either A, natural log of A, or inverse of A. then you can tell from the rate equation what the value of K is. You can determine that from the plot, right? And that's part of where we're headed in the lab. Okay. So let me see if I missed anything else of importance. Here's a good question. Yeah, we got a few more minutes. Suppose we have a reaction where we're starting off with an initial amount of A, and we go through, I don't know, 3 half-life cycles. Right? If we go through 3 half-life cycles, first half-life, let's see, this is T1 half. First half-life cycle, how much would you have left? Divided by 2, right? Second half, how much would you have left? Based on A0. Second, you would have 4, right? Divided by 4. You divide this by half, and then you divide that by half again. The third cycle of half-life, what would you have? Well, you got to divide it by half again, which means 8. Right? See the pattern? However many half-life cycles you have, what you have left over is 2 to the n, where n is the number of half-lives. So we went through 3, 2 to the third power is 8. If we went through 4, it would be 2 to the fourth power, 16. If we went through 5, it'd be a 32nd of the amount that you started with. Okay? All right. Let me scratch my head again. Let's see. I think that covers everything that I'm interested in talking about, unless you have some other items that are gnawing at your craw. Nobody? Okay. Well, you can stick around if you want to. I'm going to go back and redo that, the one that I missed recording. Here it is, number 7. Hopefully it'll be a shorter experience now because I've gone through it once. So that's, look on the bright side. The solution to number 7 shouldn't take me as much time this time, the second time around. Okay, so let me redo 7. All right. So what are we given? We're given this equation. And there. And there. And the experimentally determined rate law is the disappearance of, or change in disappearance of oxygen over time. And this is what we're substituting for rate. Rate is determined in terms of O2, right? We could have done it in terms of NO, right? It would have been a different number. but it would have been the same rate law. Should have been the same rate law. The K value, and then NO here to the second power, and oxygen to the first. Now that's coincidental. Right? Remember the overall equation, balanced equation, technically you cannot use the coefficients for the powers, the orders, right? So that's a coincidence. It just happened that way. Okay, so we have three possibilities. Excuse me. 5 possibilities, with the 5th one being none of these. So the rate determining step for A is going to be the slow one, this one, plus this one yields this one. Right? The rate determining step for B is the slow step NO3 plus NO yields 2NO2. The rate determining step for C is the slow one N2O2 yields NO2 plus O. And D, the rate determining step is the slow one, this one plus this one plus this one. And then E is none of these. None of them satisfy. Okay, remember the first condition we had to satisfy was we have to be able to add up the elementary steps, and the result is the overall reaction. And let's just say we've done that, and I'll tell you that every one of those mechanisms satisfies the first condition. The second condition is the rate determining step has a rate law associated with it that we can write from the equation. That's the unique thing about elementary steps. You can use the coefficients to write the rate law for an elementary step. And since it's the rate determining step, it should give you the empirically determined rate law. Now, it may not be directly applicable, because if you have an intermediate in your rate determining step law, then you got to get rid of it, because it won't match this one, because the experimentally determined rate law has only terms that are in the reactant side. And if your rate law for the slow step in any of these doesn't have both of those in it, in this case, then you can either throw it out, or you can find a way to substitute from other parts of the mechanisms, right? So let's do process of elimination first. O2 plus O2 yields O2O2. That's just plain stupid. I mean, that mechanism should not have even gotten past the reviewers, right? This equals that, it's obvious. That doesn't tell us anything new, doesn't shed any light on the mechanism whatsoever. We've got these three to choose from. So let's just start at the top and say, all right, so the rate law for this one would be rate is equal to NO squared, because there's a 1 here and a 1 here. Add them together, you get 2. Okay. What's the problem with this one? The problem with this one is it doesn't have oxygen in the rate law. And there's no way that we can get oxygen into the rate law, because if we substitute some other term for one of these NOs, then that NO goes away. And let's look at the possibilities. right, for A, the fast step would only have N2O2 and O2 in it. Okay, so there's no way to substitute in NO because N2O2 and O2 cannot be resolved in terms that will substitute into NO. Can't be done, right? So that X's out the first one. So now we have either B or C. So what would this one be? Well, the rate equals N2O2 to the first power, right? So that's valid, but there's no N2O2 up here. So we have to look to the other parts of the mechanism to see if there's a fast equilibrium for N2O2 and C. That's a good place to go, but it doesn't give us oxygen, right? And the other fast step for C only has the free radical O, the oxygen atom, right? So there's no way to get oxygen into, there's no way to resolve this in terms that will give us O2, right? So that lets this one out, right? So the only two possibilities are it's either B or none of these. So we've got to look at B and C if we can convert this, the rate law for the slow step into something that's experimentally determined. Right? So now we have to settle on B and prove it. If that E choice, none of the above, were not there, if we had something else there, then we would just need to choose between that one and that one. You could do another process of elimination and probably get rid of the last one and not have to do a bunch of calculations. But the evil ogre that I am, I gave you none of the above so that you would have to go in and resolve this equation. So let's put this one back up here. What did I say it was? In the slow step. So for B, the slow step is NO3. Well, the slow step, yeah, the reaction, the elementary step is this one plus this one yields this one. So the rate law for that one will be some sort of rate measurement, either disappearance of this one or that one, which really doesn't have a lot of meaning because, well, we would do it in terms of that one, of course. The expression then would be some K for this B times NO3 times NO. Okay, so that would be our rate law. Only we have one of these up here. We need two of them, 2 squared. And we don't have any NO3. Right? So we need to go back to the mechanism and see if there's a way we can substitute in for NO3 and leave us with another NO and an oxygen. So for B, the fast equilibrium does present the ability to do that. Right? If we say that a fast equilibrium means that the forward rate and the reverse rate are equal, and they're very fast. So this one has a K1 and this one has a K minus 1, right, for the reverse. Then we need to write rate expressions for those two and set them equal to each other. So the rate for the forward reaction is NO O2, right, and K1. And the rate for the reverse reaction is from this side that way. So it's K minus 1 times NO3 to the first power. Okay. Now we have something that we can substitute. If we can resolve this equation for that term, plug the equivalence of that into this, then perhaps we can get something that looks like that. So let's solve for this one. Like that. That means this one goes over here. We have K1 over K minus 1 times NO times O2. There. Now we'll substitute this into here for the NO3 right there. All right. So let me erase this. Let's just erase one at a time. So I have the rate equals, so KB, let's just do it this way. KB, and then that expression, K1 over K minus 1 times NO2, and then times this one by itself. There we go. We've made our substitution. Right. Now that we've made the substitution, I can erase this. Now the rate is, these are all constants, and taken all together are equal to K, that value. And then this one times that one is NO to the second power, and this one is O2, just like it is. So that means that B is the best mechanism because we produce from the rate determining step a rate law that can be resolved in terms of the experimentally determined rate law. So B is the answer and E's out because B works. All right. Oh, and I've still got 5 minutes left. Well, I can't think of anything else. So I'll be able to post this one shortly on Blackboard. And in the meantime, I'll work on the lab number 2 video. I've still got to correct it. I hope I don't have to do the whole thing over again. But I think there's a way I can insert corrections. And I'm wearing the same shirt today as I did yesterday, so you may not even be able to tell the difference. Okay, everybody good? Got any questions? Nope. Okay. So coming up on Tuesday is the exam for Chapter 12, and then we'll jump into Chapter 13, which will be on equilibrium on Tuesday. Okay. Let me stop the recording.